Here's a problem where we are asked to prove something. Show that the ratio of sum of first n terms of a GP to the sum of terms from n plus 1th to 2nth term, sounds like a tongue twister, is 1 by r to the power n. So I know this looks a little hairy, there are no values, it talks about terms n, r to the power n and whatnot. But I encourage you to stick with it, pause the video, try this on your own, and then we'll do it together. Okay, so whenever you see something like this, try simplifying the language before you start solving. What are we asked? We are asked to find the ratio. Ratio of what? Ratio of the sum of first n terms to something. So we can say that we need to find the sum of first n terms divided by something. Now let's see what that something is. That something is the sum of terms from n plus 1th to 2nth term. That's a lot of words. But what does it really mean? If nothing jumps to you, you can put in some values of n. Let's say if I put n as 10. That means for this GP, I need to find the sum of first 10 terms and divide that by what? Divide that by 10 plus 1, which means 11th, 2n means 20. So 11th to 20th, which means the next 10 terms. So if I do this with n, all I'm saying is I need to find the ratio of sum of first n terms to the ratio of next n terms. That's much more simple language. So this ratio is equal to 1 by r to the power n. That's what we have to prove. Do you want to now try it out? So let's do this together. We need to find the sum of first n terms to the sum of next n terms. But we have a problem here. We know how to find the sum of first n terms, but we don't know how to find the sum of next n terms. There is no formula for this. What do we do? So in situations like these, what you can do is convert something that you cannot find to something that you can find. Here's what we can do. We can write this as the sum of first n terms divided by, now for the next n terms, we can say that the next n terms will be the sum of first 2n terms. We can go up to 2n and then we can subtract the first n terms from it. And this was the magical step for this problem. Moving forward, we'll just plug in the formula and make sure that we don't make any silly mistakes. Okay, so let's do this. Sum of first n terms, that's a times r to the power n minus 1 by r minus 1, and that divided by first 2n terms. Now for 2n, we'll just replace n by 2n. We have a r to the power 2n minus 1 by r minus 1 subtracted by this same thing. This is what we have. Now let's try simplifying this. Do we see things that are common? Well, the denominator r minus 1 can cancel out and this a can also cancel out. So we have a by r minus 1 times r to the power n minus 1 divided by, in the denominator we have a by r minus 1. If we take that common, we have r to the power 2n minus r to the power n. This 1 also gets cancelled out. So this is what we have for the denominator. So cancelling this thing, we have r to the power n minus 1 by, and here again I can take r to the power n common. This will give me r to the power n times r to the power n minus 1, and lucky me, this also gets cancelled out. We are left with 1 by r to the power n, and that's exactly what we had to prove. Notice that things got more and more and more simpler as we went. So this is what we have. That's the proof, and I'm having too much fun, so we'll do one more problem. Here we go. If the first and nth term of a GP are a and b respectively, now this is the first term and this is the nth term, and if p is the product of n terms, then prove that p square is equal to ab whole to the power n. So this is what we need to prove. Here we need to find the product of n terms, not the sum of n terms. Try this one out. Okay, so let's break this down. We know that the first term is a. The next term will be a times r, and if we keep going, here r is the common ratio, and if we keep going, the third term is ar square, and so on. We'll get to the nth term, that's going to be a r to the power n minus 1, and we're given that that's equal to b. So let's mark this one. This one equals to b. No help for now, but it will be definitely useful in the proof. Now what do? We multiply all of these terms to get p. So let's do that. Let's multiply all of them to get something. And what do we get? Well, if we multiply all of these terms, we get a very big term. And what will this term have? Let's look at this carefully. We have A's and R's. How many A's? 1, 2, 3 and so on up to n. So we have n A's with n A's. And how many R's? Let's see. We have R, R square, R cube and so on to R to the power n minus 1. And if you multiply all of them, this is what we get. R times R square times R cube and so on up to R to the power n minus 1. Now the base is same. So if you multiply them, we can add the powers. We can do this. R to the power 1 plus 2 plus 3 plus so on up to n minus 1. And notice something familiar? We're solving a GP problem, but here we need to use the formula for sum of n terms of an AP. These are the first n minus 1 terms. This is going to be R to the power n minus 1 by 2. Okay. So if you multiply this with n A's, that means A to the power n. If you multiply these two, we should be getting P. So I think we have the raw material for P. Let's combine them and get to P. So P, that's equal to A to the power n times this thing, R to the power n minus 1 by 2. But are we looking for P or P square? I think P square. So let's square this. So P square, this is going to be A to the power 2n, but let's stick with A to the power n because we probably need our solution to look like this. So A to the power n times A to the power n, that's what we mean when we square things, times, now this one has a power in half, n minus 1 by 2. If we square it, this half goes away, that's R to the power n minus 1. Okay. So these three terms multiplied will give us P square. Don't worry about A to the power n, but let's combine these two. This is what we get. A to the power n times, look at the powers here. We have n here and we also have n here. And using laws of exponents, we can take this power common and multiply whatever is left. So we'll have A times R to the power n minus 1 whole raised to the power n. A lot of properties of exponents being used here. And what is A times R to the power n minus 1? Well, that's going to be B. So this is going to be A to the power n times, this thing is B, B to the power n, and wrapping this one up, combining these two will give us AB to the power n. And that's our proof.